A frozen fragment from another star is passing through our solar system right now. It's been traveling for millions of years, carrying chemistry our sun never created. Scientists have traced its path backward through the galaxy for 10 million years. And there's a question astronomers are quietly asking. What happens if it breaks apart? Not if it hits us, it won't. But what if thermal stress or sublimation causes it to fragment while we're watching? What would we see, and what could we learn? On July 1st, 2025, the ATLAS survey in Chile detected an object that would earn a rare designation, 3I interstellar. The third confirmed object in human history, known to have originated beyond our solar system. After Oumuamua in 2017 and 2I Borisov in 2019, we now have 3I ATLAS. When we say interstellar, we mean something precise. This object is not gravitationally bound to our Sunday. Its orbit is hyperbolic, a one-way path. It entered from beyond, it will leave into beyond, and it will never return. Every comet we've studied for centuries moves in an ellipse around the Sunday. This does not. The mathematics of its trajectory point unambiguously outward. That hyperbolic signature tells us this comet formed around another star in another protoplanetary disk under different conditions. It was ejected perhaps by a giant planet and wandered for millions of years through the cold and dark until this year when it drifted close enough to our sun for us to see it. The James Webb Space Telescope detected something unusual, a coma unusually rich in carbon dioxide relative to water. Most solar system comets are water dominant because they formed in our sun's disk. But this visitor shows a different signature. The CO2 forward composition suggests it formed farther from its parent star, or in a disk with different carbon chemistry, or under different ultraviolet conditions. This is a chemical fingerprint. Just as minerals tell geologists about rock formation, volatiles tell astronomers about a comet's birthplace. And this fingerprint doesn't match our system. It's an accent from somewhere else. The comet also began outgassing earlier than typical solar system comets, suggesting either more volatile composition or different internal structure, perhaps more porous. Both possibilities tell us about how comets form in other systems. Meanwhile, a team at the University of A Coruña in Spain used ESA's Gaia mission, a map of nearly 2 billion stars, and ran the comet's trajectory backward through time. Using gravitational models, they traced its likely path through the Milky Way for 10 million years. Star by star, gravitational nudge by nudge across deep time. 10 million years ago, humans didn't exist, and this object was already traveling, carrying frozen records of another dawn. Which brings us to the central question. What if it splits? Comet fragmentation is well documented. When a comet passes close to the sun, it experiences thermal stress. Ice sublimates, turns directly from solid to gas, creating outward pressure. If the comet's structure is weak, that pressure can cause fracture. We've seen this before. In 1994, Shoemaker Levy 9 broke into 20 fragments before hitting Jupiter. In 2020, Comet ATLAS disintegrated, approaching the Sunday. In 2019, 2I Borisov showed signs of possible fragmentation. Fragmentation happens through thermal stress, sublimation pressure, or rotational instability. If a spinning comet loses mass asymmetrically, that spin can accelerate until centrifugal force pulls it apart. So what would scientists expect if this visitor fragmented? First, this is scenario analysis based on models and historical precedent, not prediction. If fragmentation occurred, astronomers would observe a brightness increase. More exposed surface means more reflection and sublimation. The coma would expand. Dust production would spike, possibly by a magnitude or more. Imaging would reveal multiple condensations, distinct points indicating separate fragments. These wouldn't fly apart rapidly. They'd remain loosely clustered, moving along nearly parallel paths because they share the parent body's momentum. Over days or weeks, tiny velocity differences would gradually spread them apart. Spectroscopy would reveal changes. Freshly exposed interior material, insulated for millions of years, would begin sublimating. If interior composition differs from the surface, that difference would appear in spectral data. This would give us a cross-sectional view of the comet's structure, rarely obtainable without a spacecraft mission. Dust released during fragmentation would form a trail along the orbit. If Earth's orbit intersected it years from now, we might see a meteor shower, interstellar meteors carrying chemical signatures from another formation environment entirely. Some fragments might survive as independent objects. Others might disintegrate into dust and gas. The outcome depends on internal structure. We don't yet know. Is it monolithic, a rubble pile, a fluffy aggregate? Each responds differently to stress. But here's why fragmentation matters scientifically. Interstellar comets are time capsules from other stellar systems. When one passes close enough to study, we get a direct sample, a physical piece of another system's history. We can measure composition, isotopic ratios, volatile chemistry, and compare it to our comets. What was similar, different? What does that tell us about planetary formation diversity across the galaxy? Fragmentation amplifies that opportunity. Fresh interior material provides clearer signals with less contamination. If fragments spread into a debris stream, future spacecraft could potentially sample that material in situ here in our solar system, accessible with current technology. This is why astronomers are watching. Not from fear of impact. Closest approach is 270 million kilometers. Completely safe, but recognizing a rare scientific opportunity. JWST, Hubble, ground observatories, citizen astronomers, everyone is contributing data. If fragmentation occurs, the response will be immediate and coordinated. Spectroscopy, photometry, polarimetry, capturing maximum information before the opportunity passes. Because it will pass, this object is on a one-way trajectory out. Once beyond a certain distance, it fades from view. We may not see another interstellar comet for years, possibly decades. The mystery isn't whether this is a spacecraft or probe. It's not. The data are entirely consistent with natural processes. The mystery is deeper. How diverse is planetary formation across the galaxy? How different are chemical conditions in other stellar systems? How common are the elements and conditions that led to Earth? Every interstellar object is a data point in that larger question. When we analyze this comet's CO2 richness, we're reading a record of temperature gradients and ice chemistry in a protoplanetary disk that existed millions of years ago around a star we may never identify. When we watch for fragmentation, we're not waiting for disaster, we're waiting for revelation. A breakup would tell us about internal strength, formation processes, accretion in its birth system, conditions under which planets and comets come into being. That's the real story. Not fear or spectacle curiosity. Recognition that we're at the beginning of understanding how common or rare our system's history might be in the broader galaxy. 10 million years ago, this object was already ancient. It passed stars that have since died. It drifted through regions where new stars were forming. And in 2025, purely by orbital mechanics, it passed close enough that we could see it and ask where it came from. There's no intention in that. No design, just gravity, time, and chance. Yet in the randomness of its trajectory, there's opportunity to learn, to measure, to understand something we couldn't have known otherwise. If this comet fragments, we will watch, we will measure, we will publish. And when another interstellar visitor arrives, we'll compare and begin building a statistical picture of what normal looks like for objects from other systems. That's how science progresses, not in sudden revelations, but in slow data accumulation, careful comparison, gradual model refinement. The sky is not falling. The sky is teaching. Right now, it's offering a lesson in patience, precision, and the humility to admit most of the universe remains unknown. This comet will simply pass trailing ice and dust, visible for a few months before fading back into the dark. But while it's here, while we can study it, we should pay attention. Opportunities like this are rare. The universe doesn't often deliver samples to our doorstep. And every question we answer raises a dozen new ones about the systems it left behind and the galaxy it traveled through. If you want updates when new data is released, when fragmentation is confirmed or ruled out, when the next interstellar object is discovered, subscribe. The data is still coming in. The next chapter might arrive at any moment. This isn't just astronomy. This is the slow, careful work of learning where we fit in the larger cosmos. And that work is happening now, above your head, in the cold light of a visitor from another star